Okay, sorry about that. It cut off for some reason. Bronsted-Lowry definition of an acid or base. An acid is any substance that can donate or give away a hydrogen ion. Remember, anytime you see proton, we're referring to hydrogen ions there. A base is any substance that can accept a proton. And of course, there are certain things, or certain, I should say, entities, so water is one of them, that's called amphoteric or amphiprotic, which means that it can behave like an acid or a base. So how water will behave depends on what it is with. If it's with an acid, it will behave like a base. If water is with a base, it will behave like an acid. So it really depends on what is interacting with the water. So conjugate acid-base pairings. So a conjugate, anytime you see the term conjugate, we're referring to the products. So meaning, now that we are looking at equilibrium, so what you didn't know in grade 11 is that technically you always have an equilibrium process. Let me go back, you can see here. An equilibrium process if you're dealing with a weak acid or weak base in solution. Okay, so that's a very important point. Strong acids and strong bases don't have equilibrium. They're over 99% completion. So meaning it's basically almost all product. Okay, so it's not 100% product, but it's pretty darn close. But if you have something that is weak with an acid-base reaction, it is equilibrium. So meaning the products are now referred to as conjugates. So I'm going to use this as an example since we're here. So we have the base is NH3 and the acid is water. Now the products here, we call these conjugates. I'm going to use C as conjugate. Now you have to imagine if this were to go in the reverse, who would be doing the donating to who, or the accepting, to go back into the reactant form? So meaning for us here, OH would have to become H2O again. So in this case, our ammonium is going to become NH3 by losing that proton and giving it back to OH to make water. So now here, OH is acting like a base because it is accepting that hydrogen, and NH4 plus is acting like a conjugate acid because it's doing the giving away. So you basically call them the acid and base using the same theory, but we just add in the term conjugate, so meaning we're referring to the product side of the reaction. Okay, so notice this one, we can't do conjugate acid-base, or we can't do an equilibrium, because HCl is a strong acid. Now we're going to review which ones are strong, which one's weak, especially next week, but for now, just know that only weak acids or weak bases can do equilibrium. Okay, so the definitions here. A conjugate base is of an acid is what remains after the acid has donated the proton. So on the product side, it's what's left over after the acid has given away the hydrogen, because now it's going to have to accept it. Conjugate acid is what's left over after the base accepts the proton, because then it would have to give it away to go backwards. So here's our examples again. So this is the same one we've already seen. So this guy is a base, an acid, right? So meaning this is the direction our proton is moving. NH4 plus is now going to have to give it back to OH. So this is our conjugate acid, and this is our conjugate base. Over here we have ethanoic acid, so of course we know it's an acid, which means water, and you can see this is showing you the movement. Water in this case is acting like a base. So hydronium and ethanoate ions, for this to revert backwards, that means the direction of the proton would be opposite. So my hydronium is now my acid, but we have to call this a conjugate acid since it's on the product side. And my ethanoate is going to be doing the accepting, so it's a base, but we call it a conjugate base because it's a product base. Okay, so now we can match up what's called a conjugate acid-base pair. So meaning, what you do, it's almost like a before and after snapshot. So this NH3 is a base, and what we would do is link it up to what it is afterwards. So before the reaction began, it was NH3. After the reaction is over, it's NH4 plus. So this is a base and conjugate acid pairing. The other pairing here would be water and hydroxide. So meaning this is the reactant and this is the product after the reaction is finished. So it's like, again, a before and after screenshot. So down here, our acid would be paired up with our conjugate base. So this is before the proton was donated, after the proton had left. Water would match up with hydronium. So water before it accepted a proton, water after it accepted a proton. So these are called conjugate acid-base pairings. So that's what it's referring to here, conjugate acid-base pairs. Okay, so give this a try, pause the video. I want you to label every entity as being either an acid base or a conjugate acid, conjugate base, and then I want you to tell me the pairs. Okay, so let's see how you did. So let me get my red pen here. So you should have this guy, sulfuric acid. This guy is an acid. Water is our base. So there's our direction. You don't have to show this arrow. I just find it helpful, like even to kind of like mentally think about what's happening here. So our acid is doing the donating, water is doing the accepting. Over here, if this were to go back, it would have to give back the H2SO4. So this would now be our conjugate base and our conjugate acid. So the pairings are these here. So the pairs would be H2SO4 with HSO4, that's one pair, before, after. Water and hydronium, before, after. All right, so now we're looking at what happens with water. So water can act like an acid or a base. So with water on its own, so meaning water and water interact with each other. And actually what they'll do is basically donate a proton to each other. And it doesn't matter who does what. I mean, I have this picture has this labeled as an acid and this guy labeled as a base. But to be honest, it could have been the other way around. They're the exact same. They're both water. So what happens is our acid becomes our conjugate base. So meaning this gave away a proton. So technically, I know it's weird here, but you're looking at this. This one would become, let me match them up. This one would become our hydroxide because it's before it donated and after it already left. And this water would become our hydronium. So essentially, your products are of water reacting with water is hydroxide and hydronium. Now, why is this important? Okay, so technically water is a pure substance, yes, but you always have some amount of hydronium and hydroxide in neutral distilled water. So this is called the auto-ionization of water. So meaning basically water is in equilibrium with itself. Of course, most of the time when we're looking at water, we have other things dissolved in it. But it's important to know that just water on its own is in fact an acid and base reaction. Well, kind of weird to think about it that way, but it is. Okay, so why is this important for us? Let's start talking about some K's. So remember there's KEQ, KSP. Remember we had a whole bunch, I told you there's a whole bunch of K's coming up. So the solubility of, or I should say ionization of water, we call this a KW. But let's look at the reaction here and we're going to set up our K. So imagine, just say K. It's always products over reactants. So here is our two reactants of water and then hydronium and hydroxide are produced. So we have products over reactants. So we have H3O plus and hydroxide. Now this is actually showing you an error on purpose to remind you that water itself is a liquid. So meaning water is not included when we're doing our K expressions. Any K expression, it doesn't matter what type we're looking at, is only things that have a concentration. So meaning aqueous or a gas. So liquid and solids are not included in our Ks. So technically the KEQ for this is just our products, right? So imagine this is kind of like over 1, but we never talk about the over 1. So it's hydronium times hydroxide. So we refer to this as KW, but really it's the K for water. Now, why is this KW important? So it's actually this guy right here. So at K, I should say the K at 25 degrees Celsius, so in other words, SATP, it's a constant. So it's 1.0 times 10 to the negative 14. So this is going to become helpful to us, if you have hydronium or you have hydroxide, and it's happening, a reaction's happening at SATP, we can actually solve for the other substance. And I'll show you in this next section here. So now that we know the KW for water, of course, only at SATP. So obviously, if the temperature changes, the K number is going to change, but it's the same process as any other reaction, right? We know that K is affected by temperature. But when we want to solve for pH and POH, this is helpful because let's say we had hydroxide and we wanted to know the pH. So reminder, the pH, it's on the next slide I think too, but the pH is the negative log of hydronium, which is the same thing as hydrogen. Oh boy, this smells. So let's say we had the hydroxide ion concentration and it's SATP. We can solve for this and then find the pH. Or if we have the hydronium, we can solve for OH and solve for the POH, which is the negative log of hydroxide. So hopefully you remember that from grade 11. I'll post a video to try and help remind you of that as well, and it's here as well. So this black box is an important thing to remember because this shows you the relationship of going from pH, POH, and how they kind of interact with each other. So as I mentioned on the slide before, so pH is the negative log of a hydronium concentration. So in grade 11, you may have seen this. I think my class I did mention it was hydronium, but anywho, remember that hydrogen ions is the same thing as hydronium. It's automatically the same concentration. Hydroxide ions, you can only solve for the POH. So why is this important? Well, if you have hydroxide and you want to know the pH, by knowing how they interact, you can always solve for the other. So pH and POH together always add up to 14. So meaning, if you know POH, you can solve for pH. If you know pH, you can solve for POH, right? In general, this is just to give you an idea, but if you have an acidic solution, typically your hydronium is a higher level than hydroxide, which I'm hoping makes sense to you. Hydronium means that you have an acidic solution. The pH is lower. The more hydronium that's present, the lower the pH is. They're oppositely, like the lower the pH number, the higher the hydronium concentration. Okay? So if something is neutral, that means you have equal levels of hydronium and hydroxide. And if something is basic, hopefully this will make more sense. Also, you should have more hydroxide than hydronium because most bases produced hydroxide ions.